Current electricity for class 12. Hi, myself Dr. S.K. Bushra, former HOD, Department of Physics, Cotton University. This is a video lecture in physics for class 12 students. Lesson 6 of chapter 3 on meter bridge and potentiometer. In this lesson, we'll cover the following. Determination of unknown resistances by a meter bridge, potentiometer and its uses, and then a few tests of reasoning and numerical problems. Let's begin. Meter bridge. A meter bridge is an instrument used for measuring the unknown resistance of a conductor. Its working is based on the principle of a Wheatstone bridge. The adjoining figure shows a meter bridge. It consists of a 1 meter long uniform resistance wire fixed on a wooden plank. A meter scale is attached with the wire of the bridge. Metallic strips are used in a meter bridge to minimize the resistance of the connections. The black dots in the strips indicate the connection points. The bridge has two caps, one in the left and the other in the right, across which resistances are connected. We connect the unknown resistance Rx in the right gap, while a resistance box is connected in the left gap. One terminal of a galvanometer is connected to B, while the other one is connected to a pencil jockey. A jockey is a small metallic rod with one end in the form of a knife edge, which can slide over the bridge wire. A battery, along with a key, is connected between A and C. The jockey touches the resistance wire at D, say, and dividing it into two parts, L in the left and 100 minus L in the right. The resistance of the part AD of the bridge wire is P equal to rho into L, while that of the section DC is Q equal to rho within bracket 100 minus L, where rho is the resistance per centimeter of the wire. The ratio of the resistances P and Q may be adjusted to any desired value by changing the touch point D on the bridge wire. The four resistances are arm AB, Rx, arm BC, P, arm AD, and Q, arm DC of the meter bridge obviously form a Wheatstone bridge with BD as the galvanometer arm and AC as the battery arm. The jockey is now suitably moved over the bridge wire to such a point, a new D, so that the galvanometer current reduces to zero. The null deflection of the galvanometer ensures the balance condition of the bridge. Let the modified AD equal to L1 and hence DC equal to 100 minus L1. At the balance condition, we have R divided by Rx equal to rho L1 divided by rho into within bracket 100 minus L1. Therefore, Rx equal to as given by equation 1. Equation 1 determines the value of the unknown resistance in terms of R and L1. Remark: the accuracy of the measurement of an unknown resistance by a meter bridge is maximum when the balance point D lies somewhere in the middle region of the bridge wire. This is possible if the value of R is nearly equal to the value of Rx. Now let us pick up potentiometer. A potentiometer is an instrument used to measure potential difference. It consists of a uniform resistance wire, usually 10 meter long, arranged as a system of 10 parallel wires of equal length connected in series on a wooden board as shown in the figure below. The 10 wires of a potentiometer are usually represented as in the adjoining figure. A meter scale is fixed on the board near the last wire. However, in this diagram, we have shown the scale detached from the wooden board. A circuit consisting of a battery, a rheostat that is a variable resistance, and a key is connected between the terminal points A and B of the potentiometer wire. The rheostat is used to regulate the current through the potentiometer. Comparison of EMFs of two cells by a potentiometer. The respective positive terminals of the two given cells are connected to the terminal A of the potentiometer wire, while their negative terminals are connected respectively to the key 1 and key 2 of a two-way key. Let the EMFs of the cells be denoted by E1 and E2 respectively. A galvanometer is connected to the key 3 of the two-way key. The other terminal of the galvanometer is joined to a pencil jockey. The jockey touches the potentiometer wire at D, say. The key in the potentiometer circuit is now closed. Let the current in the potentiometer be I. The potential drop that develops between A and B of the potentiometer wire is V equal to I into R, where R is the resistance of the wire. Therefore, the potential drop per unit length, that is per centimeter, of the wire is phi equal to I into R divided by 1000. The key 1 and 3 are now closed to include E1 in the circuit while keeping E2 out of the purview. The contact point D is moved to a new position D1 so that the galvanometer records zero deflection. Let AD1 equal to L1. Applying Kirchhoff's loop rule in the mass AD1G31A, we have this equation, which is called equation 1, where G is the resistance of the galvanometer. The procedure is repeated by closing the key 2 and 3 to bring in E2 and to exclude E1. The corresponding balancing length AD2 equal to L2 is found out. Applying Kirchhoff's loop rule in the mass AD2G32A, we have this equation, which we call equation 2. Considering equations 1 and 2, we have E1 divided by E2 equal to L1 divided by L2. This is equation 3. Equation 3 allows us to compare the EMFs of the two cells which are given to us. If one of the cells is a standard cell of known EMF, then the EMF of the other one may easily be calculated from the equation 3. A standard cell is a type of specialized cells whose EMF is known to a high degree of accuracy. The adjoining figure shows a Wheatstone cadmium standard cell. The EMF of the cell at 20 degrees centigrade is 1.0183 volt. At any other temperature T degrees centigrade, its EMF is as stated. Measurement of internal resistance of a cell by potentiometer. The experimental cell whose internal resistance is required is connected in the circuit as shown in the adjoining figure. R is the resistance box. Let E and small r be the EMF and the internal resistance of the experimental cell. We refer capital R as R and small r as smaller, of course. Now K1 is closed to send a current through the potentiometer wire. Then with K2 open, the balancing length AD equal to L1 for E is found out. We have E equal to phi L1. We call it equation 1. Maintaining the same current in the potentiometer wire, K2 is now closed. This prompts the experimental cell to send a current in the external circuit. Let V be the terminal potential difference across the cell and let the balancing length AD dash equal to L2 correspond to V. So V equal to phi L2, we call it equation 2. Now from equations 1 and 2, E by V is equal to L1 by L2. We call it equation 3. For a current I and external resistance R in the experimental cell circuit, we have this equation 4. Since V equal to I into R, we have the ratio E by V as given by equation 5. Comparing equations 3 and 5, we get R plus smaller divided by R equal to L1 by L2. Or smaller as given by equation 6. Using equation 6, smaller may be calculated. Smaller, as we have indicated earlier, is the internal resistance of the experimental cell. Remark: the potential drop impressed in the potentiometer wire must always be larger than the voltages to be measured. For accuracy of results, the balance point should be situated towards the end of the potentiometer wire. Conditions above are achieved by suitably adjusting the rheostat and thereby adjusting the current in the potentiometer circuit. Let us now consider some problems. Question 1. If the drift velocity of the free electrons is very small, in fact of the order of 10 to the power minus 5 or 10 to the power minus 4 meter per second, then why do electrical appliances turn on immediately after the switch is closed? By closing the switch, we impose an electric field in the wire. This field is felt by the free electrons in the wire almost at once as changes in the electric field configuration travels along the wire with a speed that is almost equal to that of light. The free electrons therefore start drifting together immediately. An appliance is run by an electric current and not by individual slow-moving electrons. This is the reason why appliances turn on immediately after the switch is closed. Question 2. Why are household connections always in parallel to the mains? In series, the line voltage gets divided among the devices, and also the voltage available for a given device would now be dependent not only on its own resistance, but also on the resistances of other devices in the circuit. So, the devices will fail to operate at any pre-assigned rating. Again, if any of the devices in the circuit is switched off, the remaining devices will also stop getting power. On the other hand, in parallel, the same line voltage appears across all the devices in the circuit, and so the power output P equal to V by R square of a given device is fixed by its resistance only. Again, the voltage across each device is independent of the number of devices in the circuit, and one may switch on or off a particular device at will without affecting the others. However, if the circuit is overloaded with too many devices, the circuit might trip. For these reasons, the household connections are in parallel. Question 3. Two electric bulbs of rating 50 watt and 220 volt and 100 watt and 220 volt are given. Which one of the bulbs will be brighter when they are connected to the 220 volt mains in series? Household electric appliances, including bulbs, are designed to operate in parallel to the mains. The power output in parallel connections is given by, with usual notations, P equal to V square by R. This is equation 1. Therefore, the resistance of the 50 watt bulb is R1 equal to 968 ohm. This is equation 2. And the resistance of the 100 watt bulb is R2 equal to 484 ohms. This is equation 3. If connected to the mains in series, the current through each of the bulbs will be the same and the power output will be P equal to I square into R. This is equation 4. Therefore, the ratio of power output of the bulbs in series is P1 by P2 is equal to 2, as given by equation 5. Therefore, the 50 watt bulb will be 2 times brighter than the 100 watt bulb if connected in series to the mains. Question 4. Why does the brightness of the light from a bulb decrease when a heavy current appliance is switched on? Let the source EMF and its internal resistance be E and small r respectively, and suppose the bulb draws a current I from the source. Then the terminal voltage of the source is V equal to E minus I into small r, and the power output of the bulb is P equal to, as given by equation 1. Here R is the resistance of the bulb. Now a heavy current appliance, such as an electric motor, is switched on. The appliance draws a current I dash from the source. Then the new terminal voltage is as given by equation 3. And hence the modified power output of the bulb is P dash equal to as given by equation 4, and which is less than P. So the bulb glows less brightly now. Question 5. A 220 volt 100 watt bulb is connected to 110 volt source. Calculate the power consumed by the bulb. The resistance of the bulb is R equal to V square by P equal to 484 ohm, as household connections are in parallel to the mains. Therefore, power consumed by the bulb in the 110 mains is P1 equal to V dash square by R equal to 25 watt. Question 6. A heating coil is labeled 100 watt 220 volt. The coil is cut into 2 equal halves and the 2 pieces are joined in parallel to the same source. Calculate the energy liberated per second. Let the resistance of the original coil be R. So the resistance of each half of the coil is R by 2. Therefore, resistance of the parallel combination of the halves coils, which is R dash, is given by this equation. Therefore, R dash equal to R by 4. Therefore, energy liberated per second in the combination is U equal to, finally, 400 joule. This brings us to the end of the lesson 6 of chapter 3. We will discuss moving charges and magnetism in the next lesson. Till then, goodbye and thank you.